Okay, Nana. We will solve all the problematic that were given in this paper. They are 20, but still most of the 90 or 95% same. And your paper could also be their model, could be in the similar. Okay. So first one is actually a theory. Not going to talk about that. Second one, problematic question. So the question is the bar shown in figure subjected to a tensile load of 150 kilonewton. If the stress in the middle portion is limited to 150 megapascal, determine the diameter of the middle portion. Okay, so we need to find what is the diameter of this one. One is 6 centimeter, this one is also 6. It is asking us to identify the middle portion's diameter. Find also the length of the middle portion. Okay, we have to identify the length of, if the total elongation of the bar is to be 0.2 millimeter. Young's modulus is given as equal to 0.1 into 10 to the 5 per mm square. So first let us note down the given tensile load called E. Now the stress in the middle portion is stress 150. Determine, we have to identify the diameter of the middle m. Identify what is m. Also we have to find out the length of the middle portion. If the total elongation of the bar is to be, then if like each, the total elongation is t. If so, then as the force is tensile in nature, it can extend up to 40 point millimeter. Is millimeter. So 40.02, because the total elongation is limited to only 2 meters. Mil is obviously okay. Now what? So we were actually given what could be the limited stress. Okay, by the way, as we know that of here diameters were given. Okay, so whenever you see diameters means circular section. For circular section, that the area of the pi by value of can identify, obviously irrespective of we were directly given. So how do we calculate that? That stress is equal to force per pi by P will be equal to P. dm means identify, right? Now, apart from that, we were also told that elongation that can be for all the three different sections. In that case, you take all of these three sections information not exceed 40 point or 0.2 milli. We know that equation for change in length or default PL by, right? Know that the total deformation 0. Point, in that case L1 by plus E is constant for all of them, but area is going. In that case, by the way, 0. Point, please keep that in mind. Now T1 is also constant, take that out, by divided by length of the first segment. The total. That is the unknown that we have to find. In that case, these two are of symmetrical, right? You can do it. 40 minus x divided by. So now, and by the way, these areas are also what we can. Let us say L1 by plus L2, sorry, L3 can also be written as 1 as both, and A3 can also be L2. Let us suppose this can be written as 2L1 by and L2 by and by the way L1 40 minus 6 area of each one by pi by 36. Okay, because the units have to be in millimeters as the left side are in millimeters. Okay, please keep that in mind. I discussed by area of the second one, diameter, substitute that value. Whatever the value that you're, then have only one but the middle sigma or LM or X. Have pre M. Okay, substituting this value, you the first one. Now let us come. By the way, you know as proportion ultimate. What is meant? Okay, three bars made of copper, zinc, and aluminum are of equal length. Three bar of copper sections now they are rigidly connected at their ends. If compound member is subjected to a longitudinal pull of 100 kilonewton, estimate the proportion of the load carried on each rod and induced stress. What they say? Let us say these two are attached with different or or so their lengths are same. Longitudinal at the so we have to identify what is paid and what is take value of aluminum. First of all, we know that the previous problem also, the previous problem also in deformation, total deformation. That equation can also be placed here. But before that, let us see identify each rod. Load will come depending upon the induced. We also have to find. So how do we find this? So we can clearly set some equations here. We know that change in length of copper is aluminum. Let's consider is PL by equal to L by what is P here? Now that it is P, also the what is area? Area was given. E is given 1 point. EZ, that is how. By the way, in C Z, so you will get a relation C and Z, and there will be a constant. Okay, how many? So using this, can actually replace. Uh, I will explain it. So similar to that, like we have taken the relation sigma C and sigma Z, LZ, AZ, load on aluminum by length. Sigma Z have Z, which will again give you another relation times. You can do one thing. We can simply replace with a single stress given. Okay. So here entirely you are getting relations here, and apart from that, we also have an equation area of. By the way, let me explain. See, Nana, the total load that is being paid by the member 50 kilonewton. So the load shared by the copper plus load shared by the zinc rod plus or plus again load shared by the aluminum, all of these three are combinedly resisting this 250 kilonewton. As force resisted by the force resisted by the force resisted by the copper should be equal to, right? Now this PA can be written as sigma A into area plus this can be written as sigma Z plus sigma C. So what you're going to do, you're going to replace sigma A with sigma Z. Then we also have relation for sigma A and sigma C also. Then use those equations and replace with only one type of constant. Let us say the constant is K. Then with multiplied by that, and these areas were given as 500, 700 and 1000, right? I mean, we'll get, substitute this sigma C in this equation to get sigma Z. So substitute in this equation to get sigma A. Likewise, you can identify unknown value. So you know the stresses. So if you want to identify the forces, again you have to use. So once you know sigma C, we can say A by area surrounding bar. You, yeah, sorry for that. Yeah, from this equation, right? Yes, we can identify what is the load being shared by the aluminum bar, and similarly using these equations, we identify loads other bars less than the copper. So we have to draw the shear. Draw the configuration. Two to four. Let's first get some point and D. First we have to identify RD. We know that RA RD should be 30 of 50 plus 40. right? Now, let us take moment RD equal, writing them. Okay, this time yes, the force acting here would be 10. Okay, for UDL, you have to multiply the magnitude, the length. Okay, then you will get the magnitude, this intensity of. Now, this force is going to act exactly. You're taking moment 4 plus half of this force again to RD from the early, right? Here upward force will be treated as negative. Mark that upward force. Downward, I don't know if it is going up to this one, it is going to vary linear. It is going, as there is no force between B and C, then true. సరే ఇల్లు నేను చదువు క్లాస్. Okay, this now shear force is okay. Have to the bending moment. Shear force can be identified. Dimension RD. Here at this specific location, dimension 10 into RD minus. When it comes RD minus again minus 2. When it comes to this minus or 1, but no. Similarly, let us try to identify bending moment at A and D is going. Let us come right. So at point C is given by, okay, so the forces are like this. RD is acting, so whatever the point that we are considering, we have to consider it as the center of the clock. Okay. By the way, this UTL has to be converted into a point load. We do so, will act like the magnitude is given by 10 in or length into intensity. Now this dimension is acting right side. Okay, this force is, the clock is going to rotate like this. clockwise force, 40 to anti-clockwise force and RD going to be the. So similarly, you try to identify the bending moment at B. Given by RD into this distance, the distance from point B going to be 6. Okay, next minus this is the clockwise moment, 10 into 4 to is, I told you, is going to act at the middle. So point B is like this. Now point B is center of the clock. There is point C, there is 1/4. Apart from that, the UDL which is converted into a also be, and this is RD, right? What we are doing, this distance is 6 and this distance meters, this is 10 into 4, 40 into minus 2 into, okay, that is how you have to. RD is going in this direction. This 20 kilonewton clockwise direction. This is trying to rotate the beam in the clockwise. This is also clockwise, but this one is anti-clockwise. Assume this, right? That's why, according to their nature of okay. Now similarly, try to identify A and as well as, sorry, these two are fine, but you have to understand their nature, how they are going to work in, and whether they are positive or negative. By the way, this is a parabolic certain extent up to point C. From this, like this, need not to be exact, can also. And by the way, you want to solve these problems, the given link provided will create the bending moment as well as for the of explanation. Exactly a simple beam, the length of the beam 8, just for cross checking. Supports at the left, support has to be the right. Have a point load By the way, this is a dead load. See, there is distributed load. After is a varying load, you can. So this is the scenario that as you can see the bending diagram has bending moment approximately 110. You can see here the value of RA is 40 according to the problem. We haven't solved that. We haven't done the calculation part here. Please do the calculation. Give you complete analysis description. But I don't think it is in the diagrams. No, that is good. The problem. A cantilever beam of 2 meter long is loaded with a load of 3 kilo run over the length of 1 meter from the end. It also carries a point load of 5 kilo. Let us first let, let us first on the data. Cross section. Out at the end. Fails to trade at the 400 Newton. Now, with this, let us first identify what could be the maximum bending strength. So we have the equation sigma by R equal to by I, right? This one, as the dimensions were given, we can identify as the load is given, identify M, we can identify what is Y. From this, we can identify what is stress. Let us consider these. Now, first let us try to identify bending. Based on the bending moment alone, we can design. Let's say this is RA, RB. Thing in the middle, exactly. Set a distance. Now, RA, RB will be the symmetry. Each of them will the load equally RA and RB. will be equal to 200. So bending moment becomes maximum in the middle. 100 multiplied by 1 will give 200 Newton meter of bending moment. Okay, now M is equal to 200 Newton. Now what is the value of I? I value will be by, if it is a rectangular cross section, BD cube by 12. Since it is a square, B and D both are same. So 20 power 4 by 12. So from this find out what is the value of I. Next, sigma is unknown to us. Y will be equal to depth by 2. Okay. Suppose if the cross section is like this 20, then 20 by 2 is going to give distance of the fiber, outermost fiber from the neutral axis, because bending is going to be maximum at the outermost fibers and 0 at the neutral axis. Clear to you? Please to remember that it is vice versa shear stress. Now, yeah. Now we have what is the stress that was induced in the beam. So now we will replace it at the NCS, which when now we are going to make it as a cantilever beam with the material is going to remain the same. So that's the maximum standable or break ultimate stress of this length act at the end. Let us say this is right now. So from this we can identify the bending moment, or M is equal to P into, now I will be given by, now we were given a rectangular section 40 mm wide and 60 mm deep. So BD cube by 12. 40 mm wide. D cube by 12. So which will give you what is the value of I. Okay. Now we know the value of is unknown here in this bending moment. Now y will be given by, as depth is 60, y will be equal to 30. So from this we can identify stress will be equal to, already know the stress because this is the same stress which has to be. So in that case the sigma will be equal to m by I y. So this is a known value, this is a known value, I is a known value, the unknown side of m is, so you can identify at what load material is going to fail if you convert this one to a cantilever. Now T beam shown in figure is subjected to shear force of 9 kilonewton. The section, the maximum of shear stress rather distributed. Depth of the section. Okay. FA y bar by IB. Again, you can simply utilize the equations. Okay, now the next problem that we are going to solve, C section B shown in figure situation of 9 kilo. Determine the maximum intensity of shear stress rather of shear across depth of the section. Rather rough figure. the height section given in the now. So how do we solve it? To recall the how to draw the not going to let us say okay. So what we have to do? So what is the equation for the shear stress? How is it F IV? So we know that at this location, how now we have to identify what is identify. For that, can the equation how 9 kilonewton F the area of the flame Y bar here okay students we will solve problem. So the given problem is section have to determine the maximum intensity of the shear stress and rather shear stress because depth of like we have seen before the class. Let's say this, then the distribution of thing like here have to identify the stress here and the maximum shear stress at the bending stress the neutral axis but shear stress axis is identified at general equation that we have identified FA y bar by I. For doing anything, we require equation of the void. Find that. Let us y bar. So here A1 means divide them in that case. A1 area. First one 148. The y is at a height of 142 plus is 75 into 8. Y2 will be half of it, 4 mm. 140 divided by 42 plus will get value. Let us call that value as q, because I'm not going to do the calculation. It will be boring for you. Do the calculation. Let us say this is of the web, but the juncture tau max. Tau W will be given by F, 9 kilonewton all the time. A area is how much? 70 y bar. Y bar means the distance of we are losing 4 mm here. Know that actually we'll get certain value for this one respect to this is the value of q. Okay, so based on that you have to identify what is this distance. Let me call this capital R divided by I of the section. Have to identify it, for the technology that you have learned from the mechanics. Substitute the value of I, then width is going to be this 75. Will give you the shear stress the web section. Now the shear stress at the juncture will be given by the value of shear stress in the web section multiplied by width of range by width of web section. Once you know this value, substitute it here to get the, and tau max will be given by. See here, you have to identify both of these y bars individually. So let us calculate that. A y bar, find that 75 into 8 is the second one's area multiplied by the distance of, this distance, r distance, plus second one's area is 142 into 8 to half of this, because this will alone have its own individual, because we are trying to find the shear stress at that particular location. So this is going to be another component. Area of this, not one. Based on q, try to identify that. (142) minus q, whatever the value that you're going to, okay, into 8 into 142 minus q divided by 2. because this one will have its own CG, and that CG, this area CG, moments have to be taken. Now multiply it with the AY, sorry for that. So once you got that, just as identified by AY value, F was already given to you, it is always Newton. I value you have to identify it. D value is going, sorry, 8. Here 8 is the width, but before calculating uh, this shear stress in the web section, this width is 75. That's why I've given 75 here, and here at the bottom the width is 8. That width has to be given, that you will get the tau max. Tau max will be slightly above tau j. Okay, so if this is like 15, then tau max will be around like 17, 16 or something. Okay, now next one, cantilever beam, a 4-meter span, carries a UDL of 3 kilonewton per meter over its entire span and a point load of 3 kilonewton at free end. If same beam is simply supported at two ends, what point load at the center should it carry have same deflection as the cantilever? That there is a cantilever beam of 4 meters long, which is having UDL of 3 kilonewton per meter. Value kilonewton per meter. If the same beam is simply supported at the two ends, sorry, and a point load is also there. Kilonewton load is. So if same beam is simply supported at the two ends, what point load at the center it carry to have the same deflection? So the problem is if we remove this one, okay, if we remove the loads, okay, if we remove this UDL, if you remove one, and let us say this is T, and instead of giving support at this end like a cantilever, we are supporting at the two ends. If so, then what could be the value of P to have the same deflection? That is the question. This can be solved very easily. I think might have already remember some questions here. See here, if there is a when there was a point deflection, there is a point is this, and when there is a UDL, is the deflection. So in our case, we have a UDL as well as point load. So what we are going to do, deflection of the cantilever is deflection to L plus deflection UDL's deflection by much? WL cube by 8EI W point load is L cube by the way, P is this, take this one, W1 L cube. Now this is the deflection of the cantilever. We have all the information to yeah, have enough. WL cube. What is the weight intensity here? T, right? Eight plus W1, which is the load, which is the EM. Eight plus by 8 plus. Now we know that the length is right 4 12. What we are going to do, there is a point W L cube by 48, right? We don't know the value of this. We have considered this one by length left value can, that is the next one is a beam AB of an 8 meter is loaded as shown in the figure below. Determine the deflection at mid-span, maximum deflection at end, maximum deflection and slope at end A, which means theta. So what we have to do for this kind of equation? And now for these problems, telling you they all depend on the equation that you take. if you take the equation in the wrong way, I mean, if you take the wrong equation, problem is waste of time. Anyway, the equation that we will be using, actually it is m by I equal to d square y by dx. Okay? We are going to use the bending moment equation for this. For using that bending equation, we require RA and RB. So for that, take moments, put A, have RB into 8 equal to 5 into of this of gravity from RA. Newton. Obviously, RA the bending. Remember, you have to take the equation which can contain information up to maximum bending moment. That's enough. Don't have to complicate it anymore. So mostly the maximum bending moment could occur within this frame, within this span of the beam, because this span is the, I believe that it happen within. You solve the problems the second unit more and more. Obviously, you will get an idea. Let us take an x here. Let us say this is the location of x, and to say distance of x. If so, then bending moment equation would RA into x minus, because this is a clockwise moment, so that's why this will be positive. As we are calculating from the left, if you are calculating from the right, then RB into 4 is positive. Okay. Now this as 5 into, if this total is x, this portion is needed for us. If this total is x, this portion can be written as x minus 2, right? And when you multiply it with the distance, the center of gravity will lie at the middle of the span. It has to be indicated this way. So take the equation where y by dx square equal RA is x minus 5 into minus square by. Keep on solving this equation. Dx equal to 0.25 5 into by 6. Now again differentiate it. I forgot to add 0.25 x cube by 6 minus 5 into by 6 plus even x plus. Now the real problems. So your thing is, see Nana, here the beam cannot bend. Here also beam cannot bend. So at x equal to 0, y is equal to 0. And at x equal to 8, y will be equal to, y means deflection. Here it is fixed, so there cannot be any deflection. Now substitute substitute these boundary conditions in this one. This one is fine. When you put 0 here, 0 here, this entire term will become 0. But here this term will not become 0. 0 minus 2 whole to the power of 4 is there. So this is going to be 2 to the power of 4 means obviously 16. So into 5 divided by 24. So if you take out that value to the other side, obviously C1 is going to become 0 because X is going. So you can find C2 value. First you will get the value of C2. Then again substitute X equal to 8 and Y equal to 0. As you know already the value of C2, substitute it at 5. Not going to do the entire calculation. 0 cube. Here from this equation C2 can be identified. Okay. Take this equation again. Into Y equal to 5 into. Now substitute this boundary condition. Sorry, cube by 6 minus 5 into 8 minus 4 by 24 plus C1 8 plus, you know the value of C2 you got from here. Substitute that value of C2. We'll get, now you will have the deflection equation. So you can, with that you can find deflection at any location. So you were told to find, or you were asked to find the maximum deflection. So to get the maximum deflection, you have to, at the maximum deflection, suppose if the beam is like this and if it is going to deflect like this, at the maximum deflection dy by dx is equals to 0. So substitute that. Okay. As you know the value of C1 from this boundary condition, substitute that value. Will obviously get an equation, quadratic equation, either second order or third order. Okay. So based on that, basically what you can do is, if it is a second order equation, you can easily solve it using minus b plus or minus root square minus, right? But if you got third order equation, then do one thing. Here x value is varying from 0 to 8. Substitute 1, 2, 3, 4 likewise. Okay. So once you substitute those values, at a certain values there is a possibility of change of value. If it is not solvable, then you have to use Newton's Raphson method that you are learning. Then Raphson method. So there will be some initial value. So f by f dash of 0 something will be there. Use that Newton Raphson method that you are currently, so that you can identify the location where the deflection can be maximum. If it is time taking for you, write the method and leave it like that, because these problems cannot be solved within 45 minutes. I know that. Okay. Next, a beam is simply supported at the ends, is 4 meter long. It carries a uniformly distributed load of 20 kN of 2 meters, starting at a distance of 1 meter from the left and together with the concentrated load of 40 kN left hand support. Calculate deflection at the center. So problem is similar to this, but anyway I will help you with of Okay, after 1 meter, okay, what you have to identify the bending moment. For that, you have x value up to this, because within this time frame, mostly the bending moment is there, maximum bending moment, not mostly. Let us say taking x here up to this look. RA multiplied by x minus x into x minus. Okay. Now solve for this. And remember, for support x equal to tan is 4 only. So integrate it, add the constant, apply the boundary conditions, get the constants. Okay. Based on that, take the value. Okay. If you think it is taking too much of time, write the equation, governing equation for y and dy by dx. Okay. Then tell that using Newton-Raphson method, or there are some methods, other methods, but I would prefer this one. We used to solve these kind of problems with Raphson method. So using this, we can find the roots, approximate roots. So we used to do this for up to 5 digits of accuracy. That in the second iteration itself, mostly you will get the value. The first iteration, you will get the first 2 digits. I guess I think that's enough, more than enough. Nobody is going to solve this kind of problem. Okay, but as they are new syllabus, I have to now derive an equation for slope and deflection cantilever beams related to UL of 10 kilonewton per meter over the entire span. Again, there's not anything related to the dimension span. Obviously, you have to this one. Okay. So instead of starting like this, take this one with a general value, say W. Okay. So obviously, we have W L to the power 4 by 8I is there, which is what we are going to get. Obviously, but do it. So let us consider the value of x here in this direction. Now bending moment will be given by, so this W into x will give the magnitude multiplied by x by 2. Okay, so W x square by, this is going to be into equal to W into x square by 2. Okay, now integrate it, you will get dy by dx W into x square plus c1. Again integrate it, Wx plus C1x plus C2. So for this one, again take the boundary condition at x equal to 0. Again, x equal to 0. dy by dx will be. Substitute that, get the values for C1 and C2. Substitute them. Obviously, you have to end up with L to the power 4 by, which is, then substitute the value of W there. Is 10, which given in the two shafts, the same material and same subject torque.